What specific problem does the Visual Predictive Instruction Tuning (VPIT) approach aim to solve in the context of multimodal large language models? And how does it differentiate itself from existing methods like LWM, Show-O, and Chameleon?
The Visual Predictive Instruction Tuning (VPIT) approach aims to solve the problem of efficiently enabling multimodal large language models (MLLMs) to generate visual tokens alongside text tokens without requiring extensive pre-training or large datasets. Unlike existing methods such as LWM, Show-O, and Chameleon, which necessitate billions of image-text pairs for extensive pre-training and fine-tuning, VPIT leverages a lightweight fine-tuning process that builds upon the existing paradigm of visual instruction tuning. Specifically, VPIT trains an LLM to output both continuous visual tokens and discrete text tokens using a modest amount of additional visual generation data, as little as 200K samples, while capitalizing on the model's pre-existing visual understanding capabilities. This approach highlights the intrinsic link between visual understanding and generation, demonstrating that joint training with visual understanding data significantly enhances visual generation performance. Overall, VPIT provides a more data-efficient and effective method for creating unified models capable of both understanding and generating multimodal content.
How does the proposed method of Visual Predictive Instruction Tuning, VPIT, work? Illustrate the algorithm step by step, detailing how it integrates continuous visual tokens and text tokens in its training process.
Visual Predictive Instruction Tuning, VPIT, operates by extending the existing visual instruction tuning framework to enable a language model, LLM, to generate both continuous visual tokens and discrete text tokens during the fine-tuning stage. The process begins with the model taking inputs from a pre-trained vision encoder, which provides embeddings of visual data alongside text tokens. In the training phase, the model is trained to output a combination of these visual tokens and text tokens, utilizing a next token prediction paradigm similar to standard instruction tuning. To visualize the generated visual tokens, VPIT employs a diffusion model that maps the continuous visual embeddings back into pixel space. This integration allows the model to learn the synergy between visual understanding and generation, demonstrating that the ability to predict visual tokens emerges from understanding visual inputs with minimal additional training.
Can you provide a simple yet illustrative example demonstrating how Visual Predictive Instruction Tuning, VPIT, generates visual tokens? Walk through the example using its core algorithmic steps, including the input-output process.
Visual Predictive Instruction Tuning, VPIT, generates visual tokens through a structured input-output process that combines both visual and textual data. For instance, consider the input of a text prompt like, "Generate an image of a butterfly." The model first takes the pre-trained vision encoder embeddings and the text tokens as inputs. During the fine-tuning stage, VPIT outputs a combination of discrete text tokens and continuous visual tokens, where the continuous visual tokens represent the visual information of the butterfly. To visualize these generated visual tokens, the model then utilizes a diffusion model, which maps the embeddings back into pixel space, producing a coherent image of a butterfly. This process illustrates how VPIT effectively integrates visual understanding and generation capabilities in a unified framework.
What are the theoretical or practical benefits of using Visual Predictive Instruction Tuning, VPIT, over traditional visual instruction tuning methods, especially in terms of data efficiency and model performance?
Visual Predictive Instruction Tuning, VPIT, offers significant theoretical and practical advantages over traditional visual instruction tuning methods by enhancing data efficiency and model performance. Firstly, VPIT allows a pre-trained LLM to output both continuous visual tokens and discrete text tokens, which facilitates a more integrated approach to multimodal understanding and generation. This method requires only about 200K additional visual generation data when trained jointly with visual understanding data, demonstrating a marked improvement in sample efficiency compared to traditional methods that often necessitate billions of image-text pairs. Furthermore, the findings indicate that the ability to understand visual inputs directly enhances the model's capacity to generate visual tokens, establishing a synergistic relationship that traditional methods do not exploit. Overall, VPIT effectively morphs an LLM into a unified model with competitive performance on both visual understanding and generation benchmarks, while leveraging the inherent visual knowledge of LLMs with significantly less data.
How was the effectiveness of the Visual Predictive Instruction Tuning (VPIT) method validated? Describe the experimental design, datasets used, and performance metrics that were employed to demonstrate the method's success.
The effectiveness of the Visual Predictive Instruction Tuning (VPIT) method was validated through a series of experiments that involved joint training with various datasets. The experimental design included sampling different amounts of image-text pairs from the MetaClip dataset, specifically testing configurations with 1K to 5M pairs, and comparing the performance of models trained solely on visual generation data versus those trained with a combination of visual understanding and generation data. The datasets utilized encompassed visual understanding data, like image QA and video QA, visual generation data, MetaClip, and other visual data types, allowing for a comprehensive evaluation of the model's capabilities. Performance metrics included visual question answering (VQA) scores for understanding, Frechet inception distance (FID) scores for image generation quality, and clip scores to assess the alignment between generated images and text prompts. The results indicated that joint training significantly improved visual generation performance, demonstrating that understanding data enhances both understanding and generation capabilities, thus validating the VPIT method's success.
What significant outcomes were achieved with the MetaMorph model trained using VPIT, particularly regarding its performance on visual understanding and generation benchmarks?
The MetaMorph model, trained using Visual Predictive Instruction Tuning, VPIT, achieved competitive performance on both visual understanding and visual generation benchmarks. It demonstrated the ability to leverage knowledge from pre-trained LLMs, effectively translating domain-specific knowledge into accurate visual tokens, outperforming other unified models on most benchmarks. Notably, MetaMorph could generate images requiring multi-step reasoning without explicit prompts, indicating its implicit reasoning capabilities. The model's performance improved significantly when trained with visual understanding data, highlighting the strong synergy between visual understanding and generation. Overall, MetaMorph exemplifies that unified models can be developed effectively from pre-trained LLMs, achieving high-quality visual outputs with significantly less training data compared to traditional methods.